quick summary of the ideas of scaling the horizontal and vertical axes for a sine function. We start with a unit circle, circle in red, and then a smaller white circle and a bigger white circle. We first construct the red graph. At this point, the graph is unlabeled. But if we want to label the graph according to the angle theta made by a line like this as it moves around the circle, we can do so. Okay, the angle as we move all the way around the circle is 2 pi radians, or just 2 pi. Reason for that is that the circumference of the circle is the arc distance around the circle, and the arc distance for a complete circle is 2 pi. And we identify the angle with the angle in radians with the arc distance on a unit circle. So, central angle, this being the central angle for the unit circle, is 2 pi for the whole circle. Now, if we take a portion of the unit circle, if we go through an arc that's not the whole circle, and of course we could also go through an arc that's several circles and then ends up at some point, but let's just stick with an arc within the first revolution around the circle. Okay, we can specify that angle if we know just where that point of intersection is, if we know the end point on the arc, assuming we start at the positive x-axis, then we can figure out what the corresponding angle is. Now, just for a simple example, we bisect the arc between here and here as we did in constructing the sine function, the unlabeled sine graph. We get a point here which corresponds to half the arc between the x and the y-axis. Well, the arc between the x and the y-axis is equal to the arc between the y and the x-axis here, and then this arc here and this arc here, so that's 1/4 of the complete circle, and half of that would then be 1/8 of the complete circle. The angle corresponding to the complete circle, or the arc if you wish, on a unit circle is 2 pi, so that the arc is 1/8 of 2 pi, or pi over 4. We identify this angle then, this being the arc on the unit circle, we identify this angle with the arc, pi over 4. And we call that angle pi over 4 radians. Radians being the default unit of angle, we don't have to write the angles. We don't have to write the units. Theta equals pi over 4 means pi over 4 radians. Theta equals 2 pi means 2 pi radians. Okay. Now, once we've constructed this graph, we can label the vertical axis very easily. If this is a unit circle, then the point that we get when we project straight over, which corresponds to the highest point on the graph, will have a y-coordinate of 1. And similarly, the point that we get when we project here has a y-coordinate of -1, and that's the y-coordinate of the graph at the low point. Now, if we want to construct a sine function for a different amplitude, amplitude being the distance between the horizontal axis and the maximum or minimum value of the sine function, we can do that in terms of a bigger circle or a smaller circle. So I've constructed a larger and a smaller circle here. The angle pi over 4 radians applies as well to this point on the circle as it does to this point on this circle. However, it's only equal to the arc distance if the circle happens to be the unit circle. Okay, so the arc distance here is clearly less than pi over 4 because this circle is smaller. The arc distance here is clearly greater than pi over 4 because this circle is bigger, but we still say the angle is pi over 4 because the angle is identified with the arc distance on the unit circle. Now, if we have the bigger circle, it's clear that we can construct an unlabeled sine graph just as well with a bigger circle as we could with a smaller circle. So we construct that unlabeled sine graph here, and then we say, well, it looks like the radius of this bigger circle is about 1.7, let's say, times the radius of our unit circle. So that now this graph has an amplitude of 1.7. The high point is equal to the radius of this circle. The y-coordinate of the high point is equal to the radius of the circle, 1.7. And, of course, the low point is at negative 1.7. On this smaller circle, the radius of this circle appears to be pretty close to half. I would estimate 0.55, but we'll just say a half. So the radius of this circle is 0.5, so that this point is at negative 0.5, this point is at positive 0.5, and the sine function that we construct based on this circle is sketched here, and it's got an amplitude of 0.5 units above the x-axis to 0.5 units below the x-axis. Okay, well that takes care of scaling the vertical axis, and all we have to do to rescale the vertical axis for any graph is just multiply the value of the sine function by the radius of that circle. So that the graph we see here is of y equals 1.7 times the sine of theta. The graph that we see here is 0.5. Y equals 0.5 times the sine of theta. The graph of y equals 0.5 times the sine of theta. Now this is, of course, the graph of y equals sine of theta. So let's put an arrow there. If this is a graph of y equals 0.5 sine of theta, then for any value of theta, for any point on the x-axis, in other words, the y value for this graph should be 0.5 sine of theta. The y value for this graph should be sine of theta. So the y value for this graph should be 0.5 of the y value for this graph. And if you draw a vertical line anywhere along this axis, if the graph has been constructed properly, accurately, then this y-coordinate will be half of this y-coordinate. Again, because here you're multiplying sine theta by 0.5, here you multiply sine theta just by 1. You have just plain old sine theta. Similarly, the y-coordinate for this graph should be 1.7 times the y-coordinate for your sine function graph. Okay, so that pretty much summarizes how we scale the vertical axis and what the function looks like for the different scales. We haven't messed with the sine of theta because we're still going through a complete cycle up to theta equals 2 pi. And now we do want to start talking about the scaling of the horizontal axis. So why do I say theta equals 2 pi here? Well, it's because one cycle of the sine function occurs when you go one time around the circle. So one cycle is once around the circle. One cycle of the graph is once around the circle, and that corresponds to what I call a phase change of 2 pi. The phase now being the change in the angle here as we move around the circle. And we see that that angle has to be 2 pi or 2 pi radians if we go all the way around the circle. So a complete cycle corresponds to a change in phase theta of 2 pi. The phase is the angle on the reference circle. Okay, so if we just do sine of theta, the phase is theta, and the change in phase between here and here then always has to be 2 pi, whether this is sine theta or anything else. In this case, it's sine theta, so theta has to change by 2 pi to get the complete cycle. Now, we could do an alternative labeling of the horizontal axis. Okay, so now we regard the horizontal axis as our t-axis, and we say that t equals 1 second at this point. That corresponds to motion around the circle. If you want to if t is 1 second at this point, then it's clear that you're now regarding this axis as as representing the time on a clock. Okay, and when the time on the clock reads 1 second, having started at 0 seconds, we will have completed 1 cycle, which means that we've gone all the way around whichever circle we're looking at in 1 second. The phase will therefore have changed by 2 pi in that 1 second. So we say that the phase has to change by 2 pi radians during a cycle, as we've seen down here, as I just explained. So the phase has to change by 2 pi, and I wrote 2 pi radians here. I just wrote 2 pi here because of space limitations, but a phase change of 2 pi means 2 pi radians because, again, I keep repeating this, the default unit of angle is the radian, and it doesn't have to be written. It's optional to write the radians on this. So 2 pi radians means the same thing as 2 pi in this context. Okay, so again, phase has to change by 2 pi when t changes by 1 second. Because clearly we go through a complete cycle, so the phase changed by 2 pi. Had to go all the way around the circle. Phase changes 2 pi. Occurred in 1 second. Well, how could we write the phase then as a function of t? What's the phase in terms of t? Okay, well, the phase of the angle, the phase of the complete cycle has to change by 2 pi when t changes by 1 second. That's going to happen if the phase is 2 pi radians per second times t. Now, why do we have the radians here? Well, that's what the angle is going to be. Why do we have a second in the denominator here? Because when we multiply by 1 second, we want to get 2 pi radians. If we didn't have the second down here, multiplied 2 pi radians by 1 second, we'd get 2 pi radian seconds. And that's not what we need to get. We need to get a phase, just an angle. So we have to have a second down here to compensate for the second here. There are more fundamental reasons why we want the second down here. But it all comes down to the same thing. The units have to work out. We have to have a second here in order for the units to work out with the units we've assigned to this function. Okay, so now the phase is this, and the function is y equals the sine of the phase. Okay, at least our unit circle function. So the unit circle graph, y is the sine of the phase. The phase is 2 pi radians per second times t. Now I kind of had to spread that out. I did run out of space. Sine of 2 pi radians per second multiplied by t. So all this follows. I've written that out more clearly here. It's still not as clear as I'd like it, but it's y equals the sine of 2 pi radians per second times t. Now, these other two graphs also follow the same phase. Okay, as we move around the circle, the angle is the same for this circle as it is for this circle, as it is for the unit circle. So all I have to do to represent the graph here as a function of t is multiply this function where the amplitude is 1 by 1.7 to raise the amplitude to 1.7. So this function is just 1.7 times this, meaning that for any t, the y value here is 1.7 times the y value here, and that's exactly what it should be if this circle really does have radius 1.7 to the unit circle radius, okay? With the unit circle having radius 1. And similarly down here, just y equals 0.5 times the sine of 2 pi radians per second times t, half the y value of this function at every point.